the previous classes, you learned the basic concepts of coordinate geometry, like plotting different points in a two-dimensional plane using their coordinates or distances from the x and y axes. You also learned some important formulae, like the distance formula that gives the distance between two given points. For example, consider 2 points with coordinates -3, 4 and 3, 6. Using the distance formula, the distance between the two given points comes to 2√10. You also learned the formula for finding the coordinates of a point dividing internally a line segment joining two given points in a given ratio. For example, consider a point C dividing the line joining points A and B in the ratio 2:3. By the ratio formula, the coordinates of C are -3/5 and 24/5. Suppose point C is the midpoint of the line joining the given points A and B. In this case, the coordinates of point C are given by x1 plus x2 by 2 and y1 plus y2 by 2. By the ratio formula, the coordinates of point C in this case are 0 and 5. You also learned the formula to calculate the area of a triangle whose vertices are given. For example, consider triangle ABC. Substituting the values of the coordinates of the vertices in the formula, the area of triangle ABC comes to 4 square units. Now, consider the case where points A, B and C lie on the same line or are collinear points. Applying the formula, we find that if points A, B and C are collinear, then the area of triangle ABC is 0. We can also say that if the area of a triangle ABC is 0, then A, B and C are collinear points. We come across many different kinds of lines in our daily life, like horizontal lines, vertical lines, and inclined lines. Generally, we call a line an inclined line when it makes an angle with the horizontal. The same idea of the slope of a line can be extended to coordinate geometry. A line intersecting the x-axis forms supplementary angles. The angle made by a straight line in the anti-clockwise direction with the x-axis is called inclination. Here, the anti-clockwise direction is also called the positive direction. The x-axis and the lines parallel to it are called horizontal lines. If line AB lies along the x-axis or is parallel to the x-axis, then its inclination is 0. The y-axis and the lines parallel to it are called vertical lines. If line AB is parallel to the y-axis or perpendicular to the x-axis, then its inclination is 90 degrees. The inclination of a line can have a value anywhere from 0 to 180 degrees. If theta is the inclination of a line, its slope or gradient is given by tan theta. The slope of a line is represented by m. The slope of a horizontal line is 0. The slope of vertical lines is not defined. Let us learn how to find the slope of a line passing through two given points. Let P, x1, y1 and Q, x2, y2 be 2 points on a non-vertical line L, whose inclination is theta. Since the line is not a vertical line, x1 is not equal to x2. Hence, theta may be an acute angle or an obtuse angle. First, let us consider the case when theta is an acute angle. Draw perpendiculars QR and PT from Q and P onto the x-axis. Draw perpendicular PM from P onto QR. Since QR is perpendicular to both the x-axis and PM, we have PM is parallel to the x-axis. Since PM is parallel to the x-axis, angle QPM is equal to angle QSX or theta, since they are corresponding angles. In right-angled triangle PMQ, tan theta is equal to QM upon PM. Let this be equation 1. Now, QM is equal to QR minus MR or Y2 minus Y1. Let this be equation 2. Also, PM is equal to TR. This means PM is equal to OR minus OT or X2 minus X1. Let this be equation 3. Substituting the values of QM and PM from equations 2 and 3 in equation 1, we get the value of tan theta as Y2 minus Y1 upon X2 minus X1. Now consider the case when inclination theta is an obtuse angle. Draw perpendiculars QR and PT onto x-axis. Draw perpendicular PM from P to QR and extend MP to S. Since QR is perpendicular to both the x-axis and PM, we have PM is parallel to x-axis. Since PM is parallel to the x-axis, angle QPS is equal to angle QUX or theta, since they are corresponding angles. Since angle QPS and angle QPM are supplementary angles, and angle QPS is equal to theta, angle QPM is equal to 180 degrees minus theta. We can also say that theta is equal to 180 degrees minus angle QPM. Thus we get slope m of the line is equal to tan theta, which is equal to minus tan of angle QPM. Let this be equation 1. In right-angled triangle PMQ, tan of angle QPM is equal to QM upon PM or QM upon RT, since PM is equal to RT. Putting the values of QM and RT in terms of the coordinates of P and Q, we get equation 2. From equations 1 and 2, we get slope of the line is equal to y2 minus y1 upon x2 minus x1. Thus we see that whether the angle of inclination is acute or obtuse, the slope of a line passing through two given points is given by the same formula. Let us see if there is a relationship between the slopes of parallel lines. Here are two non-vertical parallel lines, L1 and L2, having inclination alpha and beta, respectively. If lines L1 and L2 are parallel, their inclination must be the same. Thus, we can say that angle alpha is equal to angle beta. Since angle alpha and beta are equal, tan alpha is equal to tan beta. By definition, tan alpha and tan beta represent slopes M1 and M2 of lines L1 and L2. Thus, we can say that if two non-vertical lines are parallel, their slopes are equal. The converse is also true, that is, if the slopes of two non-vertical lines are equal, the two lines are parallel. Now, let us find the relationship between the slopes of perpendicular lines. Here are two perpendicular lines, L1 and L2, having inclination alpha and beta respectively. Since line L1 is perpendicular to line L2 and line L1 makes an angle alpha with the x-axis, angle beta is equal to angle alpha plus 90 degrees. Let us take the tangent of both the sides of the equation. Tan alpha plus 90 degrees is equal to minus cot alpha. Also, cot alpha is equal to the reciprocal of tan alpha. Now, tan alpha and tan beta represent the slopes of lines L1 and L2 respectively. Putting these values in equation 1, we see that slopes of two perpendicular lines L1 and L2 are the negative reciprocals of each other. We can also say that the product of the slopes of two perpendicular lines is equal to minus 1. The converse is also true, that is, if the product of the slopes of two lines is minus 1, the two lines are perpendicular to each other. In this module, you will learn about mapping and transformation. You will also learn about reflection mapping, which is a type of transformation. Roll number 1.
Yes, sir.
Roll number 2.
Yes, sir.
Roll number 3.
Yes, sir.
Roll number 10.
Yes, sir.
It is clear that the class teacher here is taking attendance, and each roll number corresponds to a unique student. We can also say that every student is assigned a unique number, which is his roll number. And since no two different students can have the same roll number, it is a one-to-one correspondence. Similarly, if you look at a map of the world, you will find that each country is mapped onto a unique point in the map. And conversely, each point on the map represents only one place in the world. So this is also an example of one-to-one correspondence. And we say that the world is mapped on a sheet of paper. If you copy this world map from the atlas onto a sheet of paper in your notebook, then it is known as mapping from one plane onto another. In other words, information is mapped from one sheet of paper onto another sheet of paper. This mapping of one plane onto another, such that there is a one-to-one correspondence among all the points in the plane or in space, is known as transformation. A mapping that takes every point P of a plane alpha to a unique point P' of the same plane is known as the transformation of the plane onto itself. It is both 1-1 and onto. This mapping is symbolically denoted as alpha of P is equal to P'. A transformation that preserves lengths is called isometry. Transformation and mapping are the generalized concepts of functions in geometry. These were first introduced by a Norwegian geometer, Sophus Lie, and a German mathematician, Christian Felix Klein. There are various types of transformations in transformation geometry, like reflection, translation, and rotation, and their compositions. In this module, we will discuss reflection transformation in detail. Reflection mapping is the type of transformation that helps in getting the image of a point or a figure with respect to a given line. Given a point P and a line L, the process of finding a point P' with respect to line L is called reflection in L, or symmetric mapping with respect to L. P' is known as the image or map of P in L, or the reflection of P in L. The mapping of P onto P' by symmetric mapping in L is denoted as L of P is equal to P'. If L of P is equal to P', then L of P' is equal to P. In reflection mapping, we find the image of a given point with respect to a line. To find the reflection image of a point P in line L, first draw PM perpendicular to line L. After that, reduce PM to P' such that PM is equal to P'(M). Here, line PP' is perpendicular to line L. Let us now learn another simple method to find the image of a point P with respect to a line L. Mark the point P above the line with watercolor. Now, fold the paper along line L. Upon unfolding the paper, you will get a point which is an image of point P. Points that are mapped onto themselves with respect to a line L are fixed or invariant points. Points lying on the line itself are fixed or invariant points, since they are mapped onto themselves with respect to the line. Let us consider points A, B, C, and D on line L. On folding the line along itself, the reflections of points A, B, C, and D are the points themselves. Line L, in this case, is known as an invariant. Consider any two arbitrary points, A and B, on a sheet of paper. Fold the paper in such a way that point A coincides with point B. Now, unfold the paper. Observe the crease on it. This crease is the line of symmetry for points A and B. A line L, about which a figure can be folded in such a way that the two parts so formed superimpose each other exactly, is known as the line of symmetry of that figure. Consider an isosceles triangle. If we fold it along the line shown, observe that its two parts superimpose each other exactly. An isosceles triangle has only one line of symmetry, which is as shown. Consider a square. If we fold it along the line shown, observe that its two parts superimpose each other exactly. The square has three more lines of symmetry, which are as shown. Upon folding it along the other lines of symmetry, observe that the two parts completely superimpose each other. So a square has four lines of symmetry. A circle has infinitely many lines of symmetry. Any secant that passes through the center of a circle is the line of symmetry of the circle. Some more figures with their lines of symmetry are shown here. An equilateral triangle has three lines of symmetry. A regular hexagon has 6 lines of symmetry. In general, a regular n-gon has n lines of symmetry. Irregular figures have no lines of symmetry. For example, the figures shown here have no line of symmetry as they cannot be folded along any line such that the two parts coincide with each other. Given two lines L and M, how do you find the reflection of line M in line L? For this, first mark any 2 points, A and B, on line M. After this, find the reflections A' and B' of these points in line L. Line M' obtained on joining points A' and B' is the required reflection of line M in line L. If the two lines are given as shown, then the reflection of line M in line L can be obtained by producing line M onto itself. Such a line M, whose reflection image can be obtained by producing it onto itself, is said to be perpendicular to line L. Now, what do you think is the reflection of line L in itself? Yes, you are right. It is line L itself. This is because if we consider any 2 points on the line, then their reflections on line L will be the same. And on joining these points, we again get the same line L. So line L is a fixed line. Now, consider a line M perpendicular to line L. The reflection of line M in line L is line M itself. This is because the reflection of any point A on the line is a point A' which is on the line itself, and vice versa. Similarly, the reflection of line N in line L is line N itself. Thus, we can conclude that line L and any line perpendicular to it are fixed lines. Now, let us find the reflection images of parallel and perpendicular lines in a line L. Consider lines M and N parallel to each other and lines M1 and N1 perpendicular to each other. You saw just now that the reflection image of a line is a line itself that lies on the opposite side of the reflection line. Hence the reflection images of lines M and N in line L are lines M' and N' as shown here. Also, the reflection image of lines M1 and N1 in line L are lines M1' and N1' as shown here. So, in line reflection, parallel lines are reflected to parallel lines and perpendicular lines are reflected to perpendicular lines. Similarly, intersecting lines are reflected to a pair of intersecting lines. Thus, we can conclude that the line reflection preserves parallelism and perpendicularity. Consider two lines, L and M, and three collinear points, A, B, and C, such that C is between A and B. The reflections of points A, C, and B in line L are A', C', and B' respectively. Next, draw a line passing through A', C', and B'. Observe that all the 3 points lie on line M'. This means line reflection preserves collinearity. Also, point C' lies between A' and B', which means that line reflection preserves betweenness too. Hence we conclude that line reflection preserves collinearity and betweenness. Now, let's see what happens to the orientation of a plane by reflection in a line. Consider 4 points A, B, C, and D lying on a curve, labeled in the clockwise direction. The reflections of points A, B, C, and D in line L are A', B', C', and D' respectively. Observe that the reflections of the 4 given points lie in the anti-clockwise direction. Thus we can conclude that the orientation of a plane is reversed by reflection in a line. Consider a line segment AB of length x meters. Let us find the measure of the reflection image of line segment AB in line L. The reflections of points A and B are A' and B' respectively. On joining points A' and B', we get the reflection image of line segment AB in line L. Measure the length of line segment A', B'. It is equal to x meters, which is equal to the length of line segment AB. Thus we conclude that line reflection preserves the congruency of line segments. Now, let us see if line reflection preserves the congruency of angles. Consider angle AOB of theta degrees. Let us find its reflection in line L. The reflections of points A, O, and B are A', O', and B' respectively. On joining points O', A' and O', B' with rays, we get the reflection image A', O', B dash of angle AOB. On measuring angle A dash O dash B dash, we get theta, which is equal to the measure of angle AOB. However, the orientation of the angle has reversed, as you can observe from the figure. Thus we conclude that line reflection preserves the measure of an angle. The discussion leads us to the definition of congruent angles and congruent segments. Two segments and angles are said to be congruent if one can be obtained from the other by one or more reflections. Given 2 points in a plane, how do you find their line of symmetry? Fold the sheet in such a way that the 2 points coincide with each other, and then unfold the paper. The crease on the paper so obtained is the line of symmetry. This can also be obtained by drawing the perpendicular bisector of the line segment joining points A and B. Given angle AOB on a sheet of paper, to obtain its line of symmetry, fold the sheet in such a way that point B coincides with point A. Then unfold the sheet. The crease on the paper so obtained is the line of symmetry. The line of symmetry of an angle can be obtained by drawing the angle bisector of the given angle. Thus we conclude that the line of symmetry of two given points is the perpendicular bisector of the line segment joining them. Similarly, the line of symmetry of a given angle is its angle bisector.